So let me finish up this chapter on deadlock. This is where we left off last time, but a quick recap. So remember, the problem with deadlocks is you could try to do prevention, which is to remove one of the necessary conditions. But that turns out to be harder than in practice than it looks. So that's why people do deadlock avoidance. And avoidance is to run the safety algorithm to make sure that if you are going to grant a resource, you check to see that after granting resource, you're still in a safe state. If so, then you go ahead and grant the resource. If not, then that process will just have to wait for others' turn. Then it gets its turn. Okay. Now, even deadlock avoidance is still strict. Why? Because remember, deadlock is a subset of in the state space of unsafe states. So just being unsafe doesn't mean it's going to get into deadlock. So that means you are being more conservative, so that you, even if there's enough resource, even if there's, just because by allocating a resource puts you in unsafe state, that is enough to tell the deadlock avoidance algorithm to say, no, sorry, I'm not going to grant you the resource now. So even if I have enough, you're just going to have to wait. I'm going to give it to some other process where after I grant the resource, it's still in safe state. Okay, so it's being very conservative. So that's why there's these problems where people think, well, that's way too conservative. That's why real OSs just say, go ahead and do it, and then we periodically do detection. And detection is run on the order of maybe once every couple minutes, maybe tens of minutes or so, possibly. And so we saw, as with all the other previous algorithms, there's the single instance resource problem versus multiple instance per resource type problem. So this is where we were. We were last Monday. We were so with this, if it's single instance resource, you could use resource allocation graph, basically collapsing the resource allocation graph down to the waveform graph. You don't need the resource type because there's only a single instance, right? And now if you have multiple instances, then you run something that is actually kind of similar to that safety or Banker's algorithm we've seen before. So Banker's algorithm is more of this upper loop, right? It has the part where it does safety test, and then there's the actual resource granting decision. And so I actually have another version in the Google Doc that we can look at later, just so that it puts things in much more concrete terms. I gave you a lot of Python code, so you just have to go in, know what it's doing, and then you can fill in the rest to have a running program. Anyway, so this is where we were. So we're trying to do a detection of multiple resource instances per resource type, right? So the variables are mostly the same. So available is still the same. So available is not something you, as the allocator, can really do unless it does the actual allocation. Because that's, available initially is just how many drives you have, how much memory you have, right? So these are the actual physical upper limit. That's just given. Allocation is more of, over time, there's request, grant, resource, grant. Every time you grant, you put that into allocation, right? And then you subtract from available. Request is new ones coming in. And so you have to keep track of the number of instances that each process wants to request per type, right? So that's why it's a matrix. And so this looks a lot like that safety algorithm we've seen, right? So work and finish, right? Work is really a copy of available. We've seen that. Finish is Boolean to see if you can pick a process and then satisfy all of its requests based on well, based on what's available. So the biggest difference between this and the safety algorithm in the bankers is, remember, there was this, that there are two variables. One was max, right? Max was what's called claim. And remember what claim means? Claim is a declaration saying this is the maximum number of instances this process will ever request, right? So, and then it may be conservative, because when you say max, you better be the real max, right? Even if it happens only once in a million years, you still have to declare that max. Right? You promise never to exceed more than that many instances of resource per type for that process. So max is not there, because max is just a claim for the purpose of analysis, right? And the other is need. Need is what? Derived from doing what? The max minus allocation, right? So that means I promise never to exceed this much, and this is how much I already have. That difference is the need. So that's the worst case need at this point, right? So you don't see those two variables here. Why? Because we're not estimating, we're not analyzing the worst case. We're doing the actual state analysis. Are you stuck in the deadlock state or not? That's why you don't need to think in terms of worst case. A deadlock may already happen. You're just trying to see if there's a deadlock or not, right? So that's why you just have work is a copy available, and then initialize everything. Well, a finish is a little different, right? Finish means if there's the allocation is non-zero, then false. That means you haven't finished assigning resources to it yet. If allocation is currently 0, then you don't even consider those, okay? Because during this process, you're not gonna try to allocate more resources to any resource that currently doesn't hold any, because that only complicates things. So any process that currently doesn't hold any resource, they'll just have to wait until this particular round is finished. Otherwise, it's additional strain on the resource. So here, and they don't participate in the deadlock anyway if they're not holding any resource, right? So you simply just set their finish to true if they don't hold any resource. Now you enter the loop, so remember step 2 and 3 are in a loop, right? And step 2 itself has its nested loop to find an index such that it hasn't finished, and but then its request can be fulfilled, right? Because it's requesting no more than what's available. Work is a copy of what's available, right? And so then if no such I exists, then you break out of the loop. Right? So now, the inner loop, in the worst case, may have to go through at least one iteration. Then that's N. Now, step 3 is similar, except it's now work gets work plus allocation, and finish gets true. So if it can be fulfilled, you assume that is then can be taken back. And then you go through and see if there's additional things that can then be granted their request, right? And when you get to 4, then that must be the case where you jump from 2, because you went through all the processes and you couldn't find any that you can either fulfill their requests, either because they're all true. If they're all true, then that means they're done, no deadlock. If you had gone through a whole round and you couldn't find even one process whose request can be granted, then what does that mean? That means it's useless to iterate anymore, right? Because you've gone through one round, and even one that requests the least couldn't be fulfilled. You can unblock anybody. So that means they're stuck, right? So if there's any finish that's equal to false, then the system is in deadlock state. And in fact, all processes whose finish sub I equals false is part of that deadlock cycle. Okay, so that's the detection algorithm. So again, very similar in the code and intuition as the safety algorithm, except when we were doing avoidance, we were basing on the claim, which is the maximum possible request. That's a promise, and also the need, which is really the worst case request, right? So that was being considered. Now this is you want to check if it already happens. That's why you don't need the claim or need. All right. So as you can see, the complexity analysis is m times n squared, because for cycle detection it would be up to n squared and then m resources. That's why m times n squared. Okay, so if you need to go through just to get a good feel, well, you could go through this example here. So again, processes P0 through P4, current allocations shown in the column 3 resources A, B, C, and then this is a snapshot of the current requests. So P0 is not making more requests, and P1 is making 202 for 2 instances of A, no B, and then 2 instances of C. P2 not making requests, P3 making 1 instance request for A, and then P4 making 2 instances of request for C, right? And so is there a deadlock in this at this time snapshot? Well, if you run the algorithm, you see that, well, there is a sequence P0, 2, 3, 1, 4 that actually will result in finish of I equals true for all I. So that means for now there's no deadlock. Because just by running, and you don't actually, this is not the unique sequence, or it doesn't have to be unique sequence, right? So nobody says you have to execute. This is just one existence proof, and it will just figure itself out, right? And now, so to do this, well, you initialize just like before, and if you do, well, the available now is all 0. That means all resource instances are held, right? So then, allocation, right? Because 7 instances of A are 2 plus 3 plus 2, that's 7. 2 instances of B, so 1 plus 1 is 2. So that's why available is all 0, right? And so available 0 work gets a copy of 0, 0, 0. Right, and then false is all false. With finish is all false. And if you do first round, well, finish sub 0 is false, and then you checked to see if it's making any request. Well, it actually is not making any requests, so work is true. In fact, you can even skip this. You could have initialized this to true in the first place, right? You saw that algorithm, but we just do a similar to the previous one. And so allocation is, well, when it's not making requests, but then we add it back, right? So then, because we assume it can run and give its resource back. So that's why its current allocation gets added back to work. And that relieves the strain on the resource. So at least we have more resource, or no less resource than before. So it's marked true. Now for I equal 1, now its request 202, is it less than or equal to what's available, 010? Well, no, so this is actually a copy of that, therefore that's work, right? So it's not less than or equal to, so that means we'll come back to this later. Now try I equal to 2. It finishes still false, but then it's not making a request, and of course then that trivially is less than or equal to work, so we then do P2. And any resource held by P2 now is given back, right? Because we run it, it comes back. And so work plus equal to allocation. So 010 plus 303 gets 313. Okay, and mark it true. Then I equals 3. Its request is 100. Is it less than or equal to 313? Yes, it is. So its request can be fulfilled. And then after running it, its current allocation 211 is added back to work, 524. It's marked true. And then 002, is it less than 524? It is, and it's added to sequence. And then finally, we come back to I equals 0, skip it, I equal to 1. Now, can this request be fulfilled? Yes, it can. So now we fulfill the request for P sub 1. And then because all of them are true, we're done. No deadlock. Okay? Another example, so suppose request of process 2 is 001 instead of no request, 000, which was the previous example. So still we go from 0, 1, 2, 3, 4. 0 we knew didn't make any additional requests, so it's done, and then its allocation is added back. I is, well, we knew it couldn't be fulfilled before, so it must wait. I equal to 2, that's the new one, right? Because it was 000, now it's a 001. We couldn't do P2 in this case because 001 is not less than or equal to 010, right? Even though it has an instance of B, it's not requesting instance of B, so that's useless. It's requesting instance of C, but there's not an instance of C available, so that's why it couldn't be fulfilled. So then P2 must wait. Now I equals 3, and can this be fulfilled? No, so then so 100 is not less than or equal to 010, so P3 must wait. And then I equals to 4, 002, is it less than or equal to 010? No, it's not, because it wants 2 instance of C, but no instance of C is available, so it must wait. And then you keep looping, guess what? Nobody can have their additional request fulfilled because nobody's freeing up any resources, right? And so then you see only P0 got through because it wasn't making any requests. And it did free up some resource, but nobody else is freeing up any resource. So it's stuck, deadlock. And the cycle involves P1, 2, 3, 4. Okay? So that's how that detection works. And as you can see, definitely don't want to run this every single step of the time, right? And even every time you make a request, that seems quite expensive. And especially, I mean, we're just showing a small example, but a system can hold thousands, if not tens of thousands of resources like this, right? And so that's going to be very expensive. That's why you don't do this that often. You do it once a couple minutes at tops, right? And if you're stuck, they're stuck. So a user actually will probably notice it. But for real-time system, no, you can't do this. And so real-time systems can't afford to get into a deadlock like this. They need a lot more conservative approach, so they shouldn't even let deadlock happen and detect. They should really do prevention or avoidance whenever they can. And this would not be acceptable for real-time systems. Okay, so so in practice, deadlocks really don't happen that often. That's why your sampling rate doesn't have to be like every context switch. that's a little too much, right? Now, and so once you detect a deadlock, what do? Well, you have to then somehow resolve it, right? And so that means you have to somehow break that cycle, and so that involves picking some victim. And if you pick a victim, then it's actually very, very costly. Why? Because you might think, I can just kill that process, right? Well, no. You may have to do something more. Some processes can't afford to be killed like that, but they can be rolled back. Okay, so some programs support what's called transaction semantics. So you can think of this as that you can make a try, it's all or nothing. right? Either you get all the transaction, everything inside the transaction done, or you do none of them. So there is like a staging commit type of action going on here. A lot like when you do a bank transfer. Either if you just transfer money from account A to account B, you want to either subtract from A and credit to B, or you don't do anything. Otherwise, you have inconsistency. Who's going to pay for the difference, right? So that's a big deal there. So if you're in the middle of doing a deduction and then somehow you get aborted, well, you have to actually roll back, right, and retry. And the transaction may seem like less of a big deal, but then that's a simple transfer there. But you can imagine some transactions are much more complicated, right? And it may take minutes to do or longer. And so if you abort something, it doesn't really mean something. It doesn't mean kill the process. It just means abort that attempt. And what that means is that program probably gets an exception, and then it goes out the outer loop, and then it retries again. Okay, so that means there's some concept of what's called rollback involved here, and this actually is not the only place where things get done. So there are other rollback is used for more than just this kind of deadlock type of thing, for transactions, and even for a bunch. I know for embedded systems, or so for some other safety critical systems, they actually do this, because imagine like a satellite, right? Out in electronics in outer space. What do? You get alpha particles, you get gamma ray, you get things that can really bombard the electronics and cause bit flips. And then, so what do? Well, they need to do this kind of consistency check, and they may run multiple controllers, and then periodically they make snapshots, commit, or do consistency check. And in case that an alpha particle bombards your electronics and cause bit error, well, you could detect it at some point, and if you detect it, what do? You actually roll back, and then you retry that calculation one more time. Okay, so now that kind of mechanism is definitely not just designed for resolving deadlocks, but they're used for other purposes as well, depending on the domain of application. Anyway, now to resolve this, you have to break a cycle, but how many processes and which ones do you pick? Well, even that takes some thinking, right? And so minimally you have to break one. Hopefully all you do is break one. But the question then is, well, do you have just one cycle? If you break one, you broke that particular cycle, but are there other cycles in there that you didn't know, right? And so right, there may be many cycles in there, and so it's hard to tell which process was the root cause. Okay, so deadlock recovery is needed immediately after the detection, right? So there are several ways to do it. The simplest way is you just abort all deadlocked processes. I mean, it's that simple. Okay, I have a list from that detection algorithm. All those with the finished equal to false, I just kill them. That's not very nice, right? And that so now what else can you do? Well, I mean, if you abort all of them, you don't need further analysis. You don't need to investigate further. You just retry, and hopefully next time you restart them, they're okay. Or you could do, well, I'll just randomly pick one until, and then see if the other ones can make progress, and maybe they make a little progress, but then that remaining subset get into another deadlock, or maybe get into deadlock with some other process, right? So then, so you just testing your luck. So that's again not very systematic. You're really testing your luck. In practice, how well that works, hard to say. But but that's one of the things people do in practice. They just figure, well, what are the chances of you getting more deadlock after breaking one such cycle? Probably not very high, but it's not zero probability, right? So now, in which order should we choose? You either have to know a lot more about these processes involved, but in general, OS really doesn't. OS knows maybe a few things. Maybe there's priority associated with the process. Remember, there's different multi-level queue, right? Or in the case of scheduling, you have scheduling priority, or Unix has nice level. And so that means they get more slices. So you may go with that kind of priority, or maybe there's a different set of priorities. Maybe you want to check because CPU time is actually part of the bookkeeping of many OSs. So like when you can use the time command to measure how much time it takes a process to run from completion to completion, right, from start to finish. That statistics is available. So in choosing one, you might say, okay, well, if there is one process that's been running for a long time, it's probably likely to be much more expensive if I restart it, right? So maybe let's pick one that just started like less than 1 second ago. Worst case is another 1 second for me to rerun it, right? So that could be a heuristic. So how long the process has been executing, that could be a consideration. Also, maybe you want to keep track of some resource usage statistics, or how big the request is, the amounts of resources that the process needs in order to complete, and also how many processes are involved, and also are they interactive or batch. Now, in the case of batch programming, it could be actually much more expensive to restart them. Interactive, well, yeah, I mean, user sits there, gets a cup of coffee, comes back, and it's up again, right? And so that may be chosen as the preferred ones to abort, right? Because then it reconstructs a state, and fewer things are lost, right? So these are all possible considerations. But in the end, you got to restart something, or you got to abort something, right? That's the only way to resolve it, because you can't make more resources available, right? Yeah.
So what about to reorganize or sort the resource of the process?
It wouldn't work because we already exhaustively tried all of them. In this snapshot.
In this snapshot, if
right.
For example, if we have the process 1, and if somehow we can take away or take out one of the resource of one of the process and use it in another process, it's going to change.
Right. So you're assuming resource preemption.
Yeah.
Yeah. Well, that is kind of the milder version of recovery. Yeah. But a lot of things can be done that way. Yeah. In general, so especially for I/O devices, you really can, like in the middle of using, say, your Ethernet transmission. Yeah, somebody's holding Ethernet card, and you say, well, I want to preempt them. Well, then it's going to cause a lot of issues. Or even disk drive or printer. I'm in the middle of printing something, my paper, and then suddenly halfway into the page, your paper starts showing up. That wouldn't be acceptable, right? So maybe between pages, well, but you still wouldn't want that, right? Because suddenly one page is my paper, and then you interleave another your page, but then when I pick up a whole stack, right? So that would be kind of strange. So it's always difficult to try to preempt I/O. Other resources you could preempt, and those are probably done already. Yeah. So if it's just some state, then you could save and restore. Then that's okay. But anytime you have permanent effect, then those are much harder to preempt. Okay, so recovery from deadlock, you select the victim. Hopefully you can minimize the cost. There's some rollback involved. And so if you do transaction, that means periodically you have to take snapshots. And that's a lot like making a commit. I mean, you probably have used like SVN or Git or anything, right? There's a commit, remember? Right? That's to take a snapshot. And of course, taking a snapshot itself has some cost too. So that would not be for free. And if you can do a rollback to a previous snapshot, you actually have to do a lot more. You restart it, and then, assuming you could even restart in the first place. Right? And so, I mean, in the case of printer, I mean, if you really have to break that, then that means halfway into printing my paper, well, then suddenly it stopped printing the rest of my paper. And then your paper starts showing up. Then I pick up mine and say, what? What's this? Why is it only printing halfway? Right? So then I have to spend more time figuring out what to do. And sometimes that gets pushed back to the user. But even if you can resolve a deadlock, you still have the problem of starvation. Right? Why? Because you may just have a very unlucky process, always get stuck in the deadlock, and it happens to be the one that uses the least resource or the shortest execution time, and people always think, oh, that's the best one to pick as victim, and it always gets picked as the victim to abort, and so they never make progress. Okay, and that could actually happen depending on the phasing of the way that these processes are scheduled. So yeah, so this is always an interesting problem. I mean, it doesn't happen that much, but when it happens, it's not an easy problem to fix. Okay, so that is really what I wanted to cover for Chapter 8. And so at this point, what I can do is quickly point out the Google Doc, which I am wrapping up, so this will be posted shortly. But so I basically just posted a bunch of short questions for you to check your understanding. Right? And oh, by the way, the midterm is going to be Monday, November 18th here, and it'll cover up to this chapter. Okay. Next week's material won't be on the midterm, but that just means you may be able to prioritize how you study. Yeah. Yes, the midterm will cover up to this week's material, up to what I just covered. And I am very likely to take questions out of these that possibly even identical, maybe minor adjustment out of these review questions. So even though I don't require you to turn in these, you better have a good idea how to answer. And the way to find out is go back to the lecture or the slides or textbook even, so you can find the answer to these things. Okay. And there's problem set. This is a little longer, so but then not much more difficult. So yeah, we've seen this, right? For the case of transaction, how do you take the same code, run multiple instances, but then make sure no deadlock happens, right? In this case, you can figure out one of the 4 necessary conditions to break, and this happens to be the 4th one. And then also you need to think when the case where you may have some cycle, but that the assignment request or type of cycle, but then there doesn't have to be a deadlock, right? And now, if you really want to understand this well, you really should try to implement the code. Because looking at pseudocode, it's like, okay, I have an idea, but no. There's some details in there that you definitely will miss if you don't try it. Okay, so Now I give you the code for cycle detection. So we've seen this one gets mapped to that one, right? And but how do you do it? Well, they just say cycle detection. How do you detect a cycle in a graph? Have you taken algorithms? Yes? Okay. Then tell me what algorithm can be used for cycle detection. Okay, hint. It's an algorithm with 3 words and involves search. Something, something, search. Well, depth first search is one. And so DFS. Everybody knows what DFS is? You should. If not, okay, here's bonus for you. I used to teach algorithms too, so I give you the code for depth first search. And even graph data structure, Python doesn't come with one. I mean, you could use some other packages to give you graph, but I think my graph is much simpler, easier to understand. And even as a bonus, you get to learn more advanced Python features in this class. Great. So graph, what's a graph? Graph has vertices and edges, right? And how do you represent edges? Do you use an object per edge? No, you don't. You use a list. You use what's called an adjacency list. So here would be a way to represent a graph. I use a dictionary, so that's the name of the vertex. And adjacency list means it's a list of neighbors. So that means from P1, its only neighbor is P2. Okay? And from P2, it has 3 neighbors, so 3 edges. P2 goes to P4, P2 goes to P5, P2 goes to P3. That's how you interpret this adjacency list. Okay? So why do it this way? Because you don't have to invent yet another language. You write it directly in Python. So otherwise, you have to do another graph language. Then you have to do a parser for it. You have to do this and that, right? So this way, it's very easy to understand. But then to make it nice, you package it up in a class. Okay, so then to get its adjacency list, you can do that dictionary and then bracket the vertex name. Okay, so and you can do list of vertices. And well, I mean, I used to have a different way to do this. You could do a generator, like for I in self.g sub v yield I, but then in Python you could just do an iterator. What's an iterator? Well, iterator is an object that keeps track of that I on a list or anything that's a sequence. So then every time you can do a next, pulls it. So it's like a generator in a way. So, but it's called an iterator. Okay, you don't have to compute it, and it keeps track of that embedded I for you. And in fact, you can call the same iterator on multiple lists. So I can have iterator on one of them, and then another iterator on the same list. And each one, I could be pointing at different part of that list. Okay, so an iterator just allows you to use it in a for loop. So that's just a convenient way to do it. Cycle detection using DFS, depth first search, and I use the one from Corman, Lysason, Rivest, and Stein. That's a big algorithms book. A lot of people use that. I don't know if you use that, but anyway, well, this graph template code is slightly old, but I mean here it's a little updated on this on this Google Doc. So basically, what you do is then you check different starting points because there's not necessarily a root, and you don't know, you're not even given a root, and in fact there might not be a single root, right? It's a directed graph and might be connected from different places, and so you have to try different starting vertices. So that's what the outer loop does, and then what it does is then it's checked to see, oh, have I visited it? So if I haven't visited it, the color is white, its attribute is white, then I start a visit. But over time, you may start multiple visits because just the way graphs are connected or not connected. So then you retry the different, every vertex as possible starting vertex that hasn't been visited. But then when you do visit, well, it's kind of a recursive visit. Why? Because you go and then check a neighbor. If my neighbor hasn't been visited, no, good. Then I push it on a stack. In this case, the stack is a recursion stack, right? And then you keep going until you can't get any more. Then that's when you start popping. And then as you do, you keep track of where you came from. That's the predecessor, right? And so if you have a predecessor who has already been visited, guess what? You have a cycle. So that's how you do it, right? So, so that's that. There are several ways to do it, okay? So you can use DFS to check. And of course, you're welcome to refer back to the textbook. But I give you the DFS, try it, and look at its value. You can probably easily figure out how to do cycle detection. And it doesn't mean all cycles. It just means if you can detect at least one cycle, that's all it takes, okay? So see if you can use that as the basis for doing cycle detection. Okay, anyway, then Banker's algorithm, remember that's, Banker's algorithm was proposed by Dijkstra. You probably didn't know that, but okay, now you know. Again, not Dijkstra, it's Dijkstra, okay? Now it does need a few, okay, sorry, instructor, oh, I can't edit here. And so it does need a few things, basically to do column, to do vector-wise adding, and then so you basically just do. I mean, in Python you can. Oh, you don't actually need to do the list. You can just sum the map of lambda of x. Okay, by picking up the column. Anyway, it's the same as that. And increment vector, so that is like the work gets work plus allocation. You need a function for that. If you try to do the plus equal operator in Python, guess what happens? Well, it concatenates. Well, it makes a list, new list that's the concatenation of the two. So that's not what you want. And decrement, minus equal wouldn't work on lists anyway. So you need a function for that. Check for greater than or less than equal, right, depending on which one you want. Okay, so that's to see if you can fulfill a request, right? That's an operator. All right, and then the banker itself, well, I packaged it up in a class. So what it has is current allocation, the max, that's a claim, and total resources, right? That's the initial available minus the allocation. And so those are just put into the basically the attributes. And then if max is none, so we actually allow this to be used with or without the max, right? Because remember, detection algorithm looks a lot like that avoidance algorithm, right? So except the detection algorithm doesn't make use of max and doesn't make use of need, whereas the avoidance one requires you to provide the max, right? That's a claim, and also the need. So then those get copied and so forth. And here you have to initialize. You don't just initialize it to empty lists. We just follow the formula to fill in the array of this. Right? And then available, you have to put in your code. So read the comment, your code here. That means you write the code here. Don't just leave it as an empty list. Okay, and then the safety now false. Right? So then if you get it running, which I did, then it looks like this. So you have A and then B, A plus B. So that's just to test the vector add, and you do expect that. So you can use an assert to check your expected answer. And then A minus B, A minus equal to B, right? Check to make sure that's okay. The comparison, make sure you do all these comparison operators, and then available that, need is that, expect, and so forth. Okay, and safety. So that's would be a method inside the banker class, right? And so trace just allows you to print some information to see where you are. Okay, so that's more of your own debugging feature. And sequence, for now, you could do empty. And as you mark things to be true, you could actually add to a sequence, right? Otherwise, because if you just have the finish, then you just see a bunch of truths and a bunch of false. You have no idea what the sequence is, right? Because after the fact, you lost that sequence. So that's why having a sequence is actually kind of useful, okay? And and here, well, I am only using sequence and finish as local variables and work as locals, rather than like self dot sequence, self dot finish, self dot work. Okay, put in the work, which is really just a copy of available. And so this is outer loop and then inner loop. Inner loop, check to see, well, I even tell you which slide you can find this. Okay, so, and compare, and so you do steps 2 and 3, and then if you couldn't find one such I, then you drop out, and then do step 4. Okay. And step 4 is to check if there is any that's not finished. Okay, and then if you run it, you check the status of these different variables, or whether P0, P1, P2 must wait, or it gets granted and then continue, and then you can trace your algorithm that way, right? And resource request algorithm, that's still part of the banker's algorithm, but it's in a separate step, right? So first you, so there's step 1, 2, 3, 4, and it does call safety to see if a safe sequence exists, right? And then it does have to do not only request, but release, so that those values can be updated properly, okay? So even though the book pseudocode doesn't do some of these, you still, in order for it to run correctly, you need these additional methods to make sure the bookkeeping is done properly. Okay, so you can run the test request, and then you'll get the allocation, release, and available allocation, release, and so forth, right? And deadlock detection. So you could reuse a lot of this code. So you would write the banker in one file, banker.py, and then for detection, you can just import it and inherit from it. You inherit most of it, but you override a few things, right? So you define the detect method, which would take requests, and then the loop is very similar, but you don't make use of max and need. So in fact, you would just pass none where max was expected. Okay, that's all you need to do. And then then see how that works out. Right. So this can then call the other parts to do a lot of the same initialization. Okay, and then I included a test bench, but you're welcome to change the test bench and then trace it and make sure you understand every step how things work. And then if you run, then this case it is true, and then they must wait. Then finally, deadlock tells you. Okay, so the examples I used, I verified with, well, I did by hand and verified with my code. So it seems okay. All right, so really, I think if you have any doubts, working through the detailed steps of these algorithms will really help you understand how they work. Okay, so yeah, that's all I have. See you next week.